Should we start? Yeah. Okay. So let us revise little bit what we did yesterday. So what we started with is that we have a Hamiltonian which is minus summation over I si plus 1. Si is a variable which can take plus minus 1 values, and then this is we defined on a lattice which is of length L. You can have a periodic boundary conditions or open boundary conditions. So you have periodic boundary conditions and open boundary conditions, and we study both these examples. Okay. So what we study in these examples is that we write the partition functions. So this one has 2 to the power L configurations, and for the partition function is sum over all configurations, summation over C, summation over C PC. And summation over C PC is like, it is e to the power minus beta E of C. So that's your partition function, and that's what we wanted to study. Okay, and that we finally we get for, I will just continue with the periodic boundary condition. This is just trace of t to the power L. I think that's what we studied, and okay, and then we were trying to calculate various quantities. Okay, so what we tried, so one thing we calculate is let us say S, some k expectation value, this expectation value at k spin. So that is defined by summation over C sk e to the power minus beta E divided by Z, because that's the probability. So the main thing here, the partition function here, is that I will also write a statement, probability of a configuration is equal to e to the power minus beta E of C divided by Z. Okay, so that's, is it on? Yeah, okay. So e to the power minus beta EC divided by Z, this partition function, I mean, let me write it like that. So so that's what we calculated. Okay, so this turns out, right, I mean, if you write the full thing, this is configured. So this turns out that this is trace of sigma Z t to the power L divided by trace of t to the power L. Okay. So this is what we calculated, and we also attempted calculating the correlation function, but we could not complete. That's where we were. Okay, and then we also interpret this T like, so you have a lattice, and as if, you have a lattice, and each point as if there is a T, right? I mean, you are just putting a T here, each point there is a T, and that partition function is just put T everywhere, and this, if it is an open boundary condition, you put the boundary condition in both ends, like S1 and SL, whatever S1 and SL, and if it is a periodic one, you just put trace of t to the power L, trace of all that. Okay. So now we will okay. So at this stage, let me tell you that so can you write this probability, because so this is Z is trace of some matrices. Okay. So what I want to emphasize today, I think just now I'm changing the sequence how I wanted to teach, but I mean now I change it. So so this is the, if you write T, so your probability of a configuration is now e to the power minus beta E of C, okay, for a configuration divided by trace of T, as many T is what you have. Okay, this is on a periodic boundary condition. So it would be very nice if you can write this probability on the top as also as matrices. Okay, okay. So let us, this is a number. So this is also a number, but you are writing is a trace of something. Okay, so the configuration. Actually, let us say that so let's think of one configuration. How to do that? Right? I mean, I'm just saying that it is nice, and we'll see the applications. Why we want to do that? We'll see later when you do non-equilibrium states. systems, but it is, you know, useful, just useful at this stage to just write at least this one in terms of trace of some other matrices. Can you do that? Okay. So what you can do is that can any? I think I'm not asking you to guess. So e to the power minus beta EC. So let us think of a configuration C. Okay. So any configuration would let us say it will. So this is my review. Okay. So any configurations will look like some plus, plus, minus, minus, plus, minus, minus, plus, something like that. Okay. So now a different configuration will have a different sequence. Okay. So now whatever you write, you want to write it this equal to trace of something divided by trace of something, trace of t, right? I mean, each place it's a t, this is t to the power L, still t to the power L. But can you write it whatever you want to write, right? So if you want every configurations, this sequence has to be different because it should depend on this, whatever the configuration you have, right? So there's a simple way to think that for plus, you think of a matrix D, right? And minus, you think another matrix T. Let us call it E. Okay, or you can call the other names also, x plus and x minus. Okay, so you can call, so this configuration, this is the configuration. There is nothing by matrix here, right? I mean, it's a sequence of whatever plus and minus in a given instant of time. Like you take a picture, you get something like that. So one way you can replace it is basically replace plus by matrix D. So this will be D, D, E, E, D, E, E, D, like, you know. So that's a sequence, right? So now question that by doing this, are you representing all configurations uniquely? Yes, because each configuration is different from the other, and accordingly the matrix product, this is a matrix product, this matrix product will be different. I mean, no, maybe they're same, maybe they're different, we do not know, but I mean, no. So question is that this will be a sequence which is different, at least the sequence is that different, okay? So now only thing is that and we know that the configuration weights are different for different configuration. That depends on the energy. So these DE matrices must be non-commuting, because if they are commuting, then doesn't matter what you write. It's just D to the power k, E to the power something, right? I mean, no, that may not be the physical one. So right, I mean, no, that may not correspond to this. So the minimum one is that DE must be non-commuting matrices. Okay, so DE the commutation of DE has to be non-zero. Okay, so this is not equal to 0. This is commutation. Okay, and if you are familiar, you can call it this. Sorry, minus. Or I don't. I'll use only commutation, so there is no problem. DE equal to DE not equal to 0. So that's the only thing you want. So for every configuration, you this, and so now you can see that T. What is T then? If you have matrices D and E, can you represent T in terms of D and E? Because each configuration, you see, this is sum of, so what we write is that now I fill it up. So this is basically trace of, if the configuration is this will be D, D, E, E, D, E, E, whatever. So that's the configuration, right? For each configuration, you are writing it a product of matrices, replacing each basic unit, like, plus by a matrix and minus by another matrix. That's what you are doing. So now question that, are you getting all of them? So now if you set that T equal to D plus E, let us say that, I mean, let us check this, it works. So if T equal to D plus E, T to the power L is D plus E, D plus E, D plus E, L times, right? So one of the term is D, 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 D. That means plus, 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 plus. So sum of all of them is just trace of T to the power L. So T to the power L is sum of probability of all configurations. Okay. So now if you take D plus E to the power L, you have D, 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 E, right? I mean, all possible combinations you get, right? I mean, 2 to the power L combinations. D plus E to the power L has 2 to the power L different terms, products, right? Because they are not commuting. Are you happy with this? A plus B, right? I mean, I'm saying D plus E whole square times D plus E equal to DD D plus DE plus ED plus EE, right? I mean, they are not commuting, so there are 4 terms, 2 to the power 2 terms. If you take 3, it will be 2 to the power 3 terms. Okay, so 8 terms. So there are total 2 to the power L terms here. So they correspond to, each term correspond to weight of one configuration. Okay. So this is the sum of weight of all configurations. This is sum of weight of a particular configuration. So that's the way we define probability, and it is the same thing. Okay. But we do not. So basically, can you now identify D and E? Okay. So let us do this. E. Two of them. It is, whether it is plus or minus, doesn't matter. It can be 1 or 0. Each variable has two values. For each value, you replace it by a matrix. D need not be unique. We do not know at this stage. At this stage, we do not know. I'm just rewriting. Can we write it like that? So it's basically probability of a configuration is that the configuration replaced by a matrix product, make a trace of that, and divide by trace of t to the power L. That's the way you are doing. Okay? And I'm justifying trace of t to the power L. Actually, with this definition, trace of t to the power L is sum of all configurations, probability of all configurations. Okay? That's coming out to be true. Okay? So now can you identify this D and E, and we'll do a little bit. And okay, why I'm doing that? In Onof's lecture, for example, in quantum systems or quantum, he introduced this A dagger, which are operators, right? And if you know operators and their algebra, the whole thing can be described in terms of this algebra, right? I mean, if you know the operators, which describe your system, and if you know the commutation among them, the properties of them, which is called algebra, right? So you can, and operators are like, operator not like matrices, operators are matrices in some representation, okay? So here, this DE are like some operators, okay? So this is a complicated thing for a simple problem, okay? But that is not true when you go to other systems. There will be a complicated problem, and this will be the simplest thing, okay? Okay, we'll go there. But now it looks very complicated. Why do we do this? And I mean, this question, this is not need. For 1D Ising model, you don't need to do this. I'm just giving you a flavor of how you can do this, okay? So this is D and E has to be non-commuting in general, and T has to be D plus E. So can you identify this matrix, okay? So let us see how we write this partition function Z, okay? So let us write the partition function. So your partition function, so when you write this partition sum Z, so Z equal to summation over S1, S2, S3, all of them SL, and each of them actually take a value plus or minus, and then you have this plus, sorry, S1, why it is S1 T S1 S2, sorry, S1 T S2, this okay, the name of this T is called transfer matrix because it transfers from 1 to 2, right? I mean, this is the way it transfers. So 1 to 2, and then you have S2 T, S2 transfer S3 like that, okay, S3 like that, and you go like that, and finally you have SL T S1. Okay, so that's the matrix you have. Okay, and now you want to identify that this part, right? I mean, this part, this was an identity. Like, if you take summation over S2 here, this becomes an identity. But the whole thing, T times identity, this one you want to write as a D plus E, right? This is T times identity as identity. So let me take the S2 sum here and put it here. Okay. So this is just still T times, T is just T times identity matrix, right? I mean, this is just written, this is the way you calculate. So what you do is that S2 has two parts, like plus plus. So this is T plus 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 T minus minus. Okay. So this you can call it D because this is coming from plus part. This is coming from minus part. You can call it E. Okay. You can do the other way. So for example, instead of taking this one, there was another option. So you could have taken this one. I mean, what you are doing is that, you see, what are you doing? You have interactions, like first side interact with second side interact with third side. There is a coupling. Okay. So now when you write like that, that if your configuration is a plus minus something, you are forgetting about the coupling. You are just representing plus by this. Doesn't matter what is sitting here. If it is D, it is okay. E, it is okay, right? So just this interaction you are taking into matrix format, and you are replacing each point by a number, by a matrix which do not depend on what is there in the neighbor, right? I mean, that's your decoupling. Okay, some way you are decoupling things. Okay, so the decoupling occurs because it is only site dependent. You have to keep the information of a given site there, right? I mean, what is there at S2? So S2 appears here. So you take all the terms which is to S2, but you have to take a T along with it, because then T is D plus C. So you can T from the left or T to the right. Okay. So right, I mean, so another one could have been, so for example, this was S3, this one S3, and the T could have been taken like that. This one could have been also taken, right? I mean, so T equal to T times I you can put from this side or from that side. Okay, so you can, one representation you can say that somebody said that it is not unique. So D equal to T plus plus and E equal to T minus minus. Okay. No, we don't have an interpretation. The matrices which represent the spin, just represent the spin in the steady state. Why do you want to name it? No, some name, just name it your choice. Make some matrix. Representation matrix. Okay, let us name it representation matrix. Here also it is written as, every matrix can be written as Ket-Bra. So any matrix, right? I mean, I don't know, I am not getting the question. So any matrix M can be written as Mij of any dimension I, J, right? Summation of I, J. Mij are numbers, Ij are standard vectors, right? I mean, this is standard representation of matrices. Yeah, 2 cross 2 by 2 spins. That's a yes. Why? I just say that, you know, because probability is something like that. It is kind of, you know, for me, it's currently it is just a decoration. I'm just saying that I want to, because the denominator you have, all you are doing is the trace of D, like, you know, whatever, T, and if you can write each configuration by a product of matrices, you don't have to keep track of what is going on in the you don't have to keep track that. The usefulness you will get quickly now. Okay.
Please bracket. You are not giving any particular.
No, and other thing. So I'm just saying that, you know, of course you can represent this. Like, you know, there is other one. For example, if you represent it by vector, right? So don't get confused with that one. So what you have is that you can take it as a vector, and then you can, there is no vector, there is no product just like that, right? You cannot write vector after vector. It's not a simple product. Okay. You can write a direct product. That also gives you this 2 to the power L space. Okay. So that is another one. So I'm not talking of the space and evolution. The matrix remains 2-dimensional all the time. Okay. All I'm saying is that we have a number, probability is, right, I mean, you know, this one, e to the power minus beta is a number. Can you get it from some simple matrix? And the matrix has a meaning. Okay. The meaning is that only information is configuration, and the configuration, whatever configuration, is replaced by some matrix. In this case, you can get the representation of what the matrix is. Right? I mean, it's 2-dimensional. It is just simple. And in later on, I will show you how to get these matrices starting from the dynamics. Okay. Here. Okay, here you don't have it, you know, I've not talked about the dynamics yet, okay. So here, I don't know whether making sense to people. So I'm just saying here you don't have a dynamics. I mean, you start with the Ising model and directly you write the partition function. Actually, in, you know, either in simulations or in, in reality, the system, you have a system, the system evolves with some dynamics and it reaches stationary state, and you have to find what is the stationary state. This kind of questions you should ask, right? I mean, how it goes and where it goes. But the stationary state here is the equilibrium state, and for equilibrium state it is already known. You don't have to evolve the system to know what is the stationary state. You know that it is per minus beta E. Okay, that's the advantage. So here it is the advantage that you know this equation already. Okay, so it's not that you are always lucky to know this equation a priori. You have to find them. So then it will be helpful. So why I am doing it here? Here it is unnecessary. I am just representing it in a different form, which looks very spurious, but this is the simplest thing, and I can use it later. That's all I'm doing now. Okay. So this is one representation. Other one is that D equal to plus plus and T, and E equal to minus minus T. So you can take this way or that way. So both of them are equal representation. Do you know what are the matrix? D matrix is what? This one. So the T matrix equal to e to the power beta, e to the power minus beta, e to the power minus beta, e to the power beta. So what is your matrix D? That is this one, but you have to multiply with T, na? So if you multiply, so T can be written as also like, in that form. So we can see that only the columns survive. Okay, so D, so in this representation D equal to, this is e to the power beta, e to the power minus beta, 0, 0, and E is the other part. Okay, so E equal to just 0, e to the power minus beta, 0, e to the power, this equal to e to the power beta. Okay, this is, and this one is little different. So this equal to e to the power beta, e to the power minus beta, 0, 0, and this is equal to e 0, 0, e to the power minus beta, e to the power beta. Okay, so there are two different representations of the matrices. Okay. So what is the advantage you get? Okay. S3, S3. I just take a T along with it. S3, S3, T. But that is same thing as S4, S4, T. Yes, yes. Any of them, because each of them, now it is independent of the site, right? All you have, I tell you a configuration, doesn't matter which site, first site or second site or fourth site. You replace the corresponding. So I'm just saying that, now it is, once you know this, how to represent a configuration. Okay. So if I say that probability, so let us write that P equal to D plus E. So now the probability of a configuration, let us say minus plus, plus minus, minus plus, plus, whatever I write, this one. Let us say this or some other nodes. What is this probability of this configuration in stationary state? It's easy to write now, technically. So what you do is that this is just trace of D, 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 right, like that. And write, E, D, D, E, D, E, 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 divided by trace of T to the power L. That's the configuration, right? You don't have to calculate the energy. The all information what you need is already encoded in D and E. Once you know these matrices, any probability of any configuration, you can write just like that. And while writing this, each site you are replacing by a matrix. Nothing more, nothing less. You are not looking at what is in the neighbor, what you are going to write in the neighbor. The matrices are independent of the site, they are independent of the dynamics. No, they depend on the dynamics somewhere, but everything is encoded in D. Okay. So each probability of each configuration, you can write it very easily. Okay. So that's the way. So now, if I have to ask, let me repeat this calculation of SK average. Okay. Again.
So, energy depends on the neighboring site. Right?
Energy depends on the neighboring site. So somehow this D, how do I construct D? Right. I manipulate. Little bit cheating I did, right? Because I know T, and I know that T plus T equal to, if I write D plus E, then you get all the configurations. I am writing T, split T into two parts, called 1D, 1E. D has to be same as T.
D and E will depend on how many interactions are there.
No. Even if the simple interaction, I will show you somewhere that with a simple interaction, you can have infinity dimensional matrix. No, minimum dimension. Minimum, of course, any dimension is 2, otherwise it's a scalar. No? I mean, otherwise the problem is trivial. It's just simple product.
If D is say 1 plus 1, then what is the purpose?
The purpose will be lost. So question is that D equal to 1 plus 1 means all configurations more or less all configurations are the same weight, right?
Sir, we don't get like that because it depends on the S2 we are considering.
No, S2, 2 is not there. 2 is not there. We have replaced 2.
S2 or S3,
Or what, right?
constructing D is based on S2.
Yes.
The same dimension will be carried by D.
Yes. Here it is 2 dimensional. But when I think this is confusing at this stage. What was the problem? There are some problems where the problem is simpler. For example, if I have instead of Ising model, okay, I take a model which is just particles, simple particles on a box, right? These are the sides, and there are particles which are just moving left, right. Or there are many particles like random walkers. Okay, they can go to left and right with equal probability. Okay, and each particle is just doing that. In such situation, right? There are many. I don't know how many particles are there. You put whatever number of particles on a lattice, which is the ring, and then if you ask it to evolve, right? Because each site is same, and all particles are equivalent. All configurations will be equivalent here, right? All probability of all configuration will be same. Okay. So it will just depend on the number of, right? Number of particles, whatever number of particles you have. So probability of all configurations will be same, but the number of configurations is just choose n out of L. So the probability is just 1 by this. Okay. So on configuration has the same weight. So in that case, D and E become scalar, 1 by 1. No, wait a minute. Let me. Whether he got it? Did you get this? What I said? I'll come back to this question. But did you get what I said? So I'm just saying that it is possible if you have many particles. If there are n particles in this, okay, and if I want to write they're just moving left, right with equal probability. So that is same thing as Ising model as infinity temperature. Some way, you do not know at this stage how, but this is Ising model at infinity temperature, where all spin flip whichever way they like.
Like a coin having both tails.
Both head and tail. So basically n particles in this one, and they're diffusing just in the system. So all configurations will be equally likely, right? There is no way to distinguish one configuration from the other. So the number of configuration in this just CLN. Okay, so this is equivalent to LN if you are familiar with the other notation. CLN, right? You choose this many configurations. So the probability of any configuration C, this equal to just 1 divided by CLN. That's the probability, because the sum of all configurations become 1. This is for this problem, this is the one. So in this one, I have n particles means 1, 0, 1, 0, 1, 0. So each of them I write D and E. So doesn't matter what configuration I add. I want that for all configuration it has to be same. So how many D's will be there in a configuration? Right? Take a configuration 1, 1, 1, 0, 1, 1, 0, 0, 1, 0, like that. So if I replace it by D, so D, 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 E, D, D, like that. Okay, but I know and trace. I have to write the probabilities trace of this and with some constant here. But how many D's are there? N D's. Okay, so doesn't matter where they are placed, I should get one number. So that means that this D E must be commuting, na? So if they commute, then you can represent it by a number. So if I call it D, all D, so this is all of them will be just equal to this configuration is this. So D to the power n, E to the power L minus n, right? Trace of that. So if they commute, it is just that. For any other configuration, it will be just this, na? If you write any other configuration 1, 0, 1, 1, 0, 0, 0, 0, 1, 0, something like that, this is also the same. Okay. So in this case, the representation of a matrix is one by one scalar. Right? The commuting means you can replace it by just numbers. Okay. So you can have simple problems where the matrix has a dimension 1. That's a number. Okay. It's a simple problem I discussed. But this problem is not like that. Here, 2 dimension is required already. Okay. So what will be the dimension of matrix in a given problem? Those kind of questions will, we'll ask if we can go there, right? If you can follow, right? If you can go there, we'll ask such questions there.
No, sir, it's evident from what you have explained. When it is D is
No, I think we come back to this. So now, right, I mean, you can it is nothing to do with, okay. So the point is it because the dimension, I just tell you, is it because the dimension of D is 2 because S can take 2 values?
Yes.
Are you saying yes? I'm saying I'm giving you one example which contradicts. So I'm just saying, so take this, H equal to minus summation over I SI H. Okay, you don't need it. Just one dimension will work. Just a numbers will work. Okay, so D is just e to the power beta H. That's it. So in this case, D, because you know it's a simple. So here D is just e to the power beta H. E equal to e to the power minus beta H. I mean, this is, I'm not writing anything with identity. So this is scalars. All the spin can take whatever values, 1, 2, 3, 4, whatever. Okay. I mean, whatever means that many matrices you need. So if S takes 3 values, you need D, E, and something else, A, right? For 3 values to represent 3 values. So correspondingly, you have the values, right? No 3 dimension. I think I'm confusing. I do not know. I think it's not useful. Maybe I skip this. Yeah, okay. I don't know. I mean, if it is too confusing, let us drop these discussions, right? I mean, I don't know. Is it too confusing? Because this discussion, I do not know. Because then I will do something else, right?
No, but first maybe you should ask them whether it's clear. Okay, so here you are representing things by 2 cross 2 matrices, and the objective is to find a matrix D and a matrix E so that you can write the numerator as a trace of products of matrices, right? In this case, you need 2 cross 2 matrices. In actually that case, you need 1 cross 1 matrix.
Yes.
Okay,
so the dimension of the matrix do not depend on the value of the spin, value that the spin can take, number of values the spin can take. It doesn't depend on. What you want is that if the number of values the spin can take is, let's say 5, then you need 5 things to represent, 5 matrices. You need 5 matrices because the configuration. So let us say that SI in this case, I do not know what the Hamiltonian. Don't think of it as a spin. Let me call it Ni. Okay. Now let us do this for to some extent so that we know what we are talking about. So if H equal to this, so what is the partition function? Can anybody write the partition function? So the partition function is just e to the power minus beta, and Ni can take all values. Ni can be 0, 1, 2, let us say, okay, 1, 2 up to q. This is the value it can take. So in this case, e to the power minus beta summation over I Ni, right? And that's your e to the power minus beta and plus h, so plus beta h. That's your e to the power minus beta e, and then summation over all configurations, summation over all n1 and ni, okay, all ni, okay. So n1 can be 0, 1, n2 can be 0, 1. So here you can do simply you can do this calculation because this ni is just, this is equal to summation over all ni, and this is e to the power beta h n1, e to the power beta h n2, like that. So now this ni means n1 sum, n2 sum, and n3 sum. So what you do is that the sums I take it separately. This is n1, this is n2, like that. This is n3, like that. Okay. So now what you have is that this sum is gone because each of them I have written it here, and n1 can take possible values 1 to q. Okay. So basically the partition function is that n1 equal to 1 to q. So e to the power beta h plus e to the power 2 beta h plus e to the power 3 beta h. Okay. So all this up to e to the power q beta h, and then each of them you get the same term. So there are L such things to the power L. That's the partition function. So the probability of getting, let us say that probability of a configuration is equal to e to the power minus beta e of c divided by partition function. Okay. So let us see what it is. Let us take a configuration, one particular configuration. Okay. So let us, the configuration is this. So now it is 1, 2, 2, 3, 1, 2, 2, 1, 1, 2, 3. Let us say q equal to 3. Some configuration I am writing. Because the n can take any values and there are L lattice side. Each side I can take any one of the value, 1, 2, 3, whatever I write. That's I write. So how I want to represent it? 1 will be represented by some matrix called D1, 2 will be some matrix D2. So the configuration, for this configuration, probability I want to write probability equal to D1, D2, D3. I don't know what the dimension of the matrix at this state. D1, D2, D2, D3, D1, like that. So this is trace of that divided by the partition function. Partition function is whatever I have calculated. So this divided by Z. That's my partition function. But you know what is the probability of this configuration? Because probability of this configuration is the energy of this configuration. But energy of this, e to the power minus beta, energy of this configuration. But just because this is a single side problem, summation over I ni, energy of the whole configuration is thus energy of this plus energy of this plus energy of this plus energy for this. Energy of this is e to the power beta, right? And this one is e to the power, no, sorry, this is, this is energy of this is 1, energy of this is 2. So 1 plus 2 plus 3 plus 4 plus this plus that, whatever you get, and then you just e to the power beta h. So basically probability of this configuration is e to the power beta h summation over I ni. So this means 1 plus 2 plus 3, 2 plus 2 plus 3 plus like that, divided by z, that you know, right? So this one of course is a scalar, so you can d1 you can say that e to the power minus beta h 1 beta h, d2 is e to the power 2 beta h, d3 is e to the power 3 beta h. So the spin can take as many values, but d and e are taking only scalars. Is it clear now? Is it okay? So dimension of the matrices in this represent, I want to represent it exactly like that. What is the utility? You know, maybe at this stage you are not seeing the utility. I will tell you in a second. Wait for that. Right? If you write it like that, there is a very nice utility. You can easily write, this sigma g people are confusing earlier, or whatever, those things will not come. It will be very nice because each matrix is a representation of the site variable at a given site in the stationary state. So it will be very easy. So if you want to calculate correlation function, it will be very, very easy. Any function, it will be very easy. Okay, so we will see that. It's fine now. Okay, so I'm just saying that firstly the dimension of the matrix, the representation of the matrix, all these things we do not know at this stage. They can be anything. All we know is that if the site variable takes 5 values, the matrices in number it has to be 5, because each one we want to represent by something, including the vacancy. If you call 0 as a vacancy, okay. So whatever values you can take, that many matrices you want. That's very simple. And if you have a given, it's the independent. So look, I do not. So look at the utility. I'm not at this stage. I'm not talking of any dimension, any model, anything. Okay. Hamiltonian also I do not know. Okay. So but my representation I can always write it. You see. So now right. It is independent of any model. That firstly you get out of the model itself. Firstly. By doing this, you are getting out of the model, right? All you know is that the lattice has some 5 variables, right? So let us see that if your lattice has some model, like this is n equal to 1 to q, but not this Hamiltonian. I do not know the Hamiltonian. Let us say that I do not know the Hamiltonian, some Hamiltonian like that, but I do not know. I do not know the Hamiltonian, some Hamiltonian, h equal to whatever you feed in. I don't know. Okay, but this equation. This z also I do not know at this stage, but z I know what is z, right? Z can always be written z because this is sum of all configurations. So this will be d1 plus d2 like dq. Okay, there is no e. And these e's are gone because d all of them are I'm representing because 1 to q. So there are 1 to q. There is no names because there are 2. I was calling 1d, 1e. If there are 5, I call d1, d2, d3, d4. Maybe d5 is e, whatever. So z is this to the power q trace, sorry, to the power l trace. Okay, is that fine? Because this is all you want is sum of all configurations. That's your partition function, and this one will give you sum of all configurations because d1, 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 d2, all the configuration will come here. Okay. So irrespective of the model, I do not know what is the Hamiltonian. I think
the easiest way may be to say that these matrices are now your states or whatever.
These matrices are now my states. Okay, irrespective of the dynamics. The dynamics will determine what is the property of the matrices, what is the algebra they satisfy, what is the dimension, and what kind of minimal dimension, all kind of questions you can ask. But independent of whatever the Hamiltonian, I can always write probability, right? I mean probability of a configuration which is equal to 1, 2, 3, 1, 1, 2, 3, 1, 2, 2, 1 something. This equation is always true for any model. This equation is always true for any model. So that is not something which you have known earlier, right? I mean, that is one advantage. It's irrespective of the model now. Okay. So the model will tell you what the dimension of the D and things are. So this is actually trace of just write D1, D2, D3 like that. Like each one you write corresponding index. These are matrices. Divide by trace of D1 plus D2 plus up to DQ, all of them to the power n. This is always true for any model. So that is a great advantage, right? I mean, at least already you see that this is a great advantage.
Suppose our model is SI, SI plus 1, SI plus 2 type of thing.
It is still. No. No, but I mean, I did not specify what is the model. No, even SI plus 1, SI plus 2, SI plus 4, SI plus 5, whatever. I don't know. I don't need to know. I'm saying that doesn't matter what the model is. Eventually, what you are looking at? You are looking at probability of a configuration. The configuration is specified, right? I mean, something like 1, 2, 3, whatever. Right? Doesn't matter what the model. That probability is trace of corresponding matrix product. Like because each one site variable you can represent by whatever you want. Energy is not there. Energy will go somewhere else.
But D will depend on the.
So that will when I want to calculate actually what is D. Of course, Hamiltonian is needed. How to calculate it, that's a different question. But this equation is still true. The dimension I do not know. Is this part clear now? It was very hard. No, okay, anyway,
Just one question. So if you instead looked at the two-dimensionalizing, then this is hard to do.
Yes. So Ornov's question that can you extend it to 2 dimension? Okay. This is hard because 2 dimension site variables are placed on a square. Let us say square lattice. So it is placed on a square. Even if you represent them by matrices, there is no operation, right? So if you represent, so on a lattice, so the site what are you replacing? This one you are replacing by D1. This one you are replacing by 2. So if it is a 2-dimensional one, okay. So the 1 will be here 2, 3, 1, 2, 3, 1, 3, 3 like that, something like that. So this one would correspond to this one will be D1, D2, D3, D1, D2, D3. Okay. So there is no operation. I mean, I don't know how to. There is no operation in matrices which tells me that. But if it is 1-dimensional, that I can just take it as a simple product or even a direct product. I am using a simple product. Okay. So there is an operation which I can use which makes my life simpler. Okay. But in 2 dimension, you think about it, right? I mean, I am also thinking about it. No, you think about it. Like can you construct a operation, in 2 dimension, which is right? I mean, which should have this vector space property, some operation in 2 dimension. That would really be very useful. In mathematical structure, it is not there. I don't know whether it is possible, not possible. Open question. Great. Anyway. 2D thing can be solved by transformation.
This D1 is somehow related to transform. And if D is equal to D plus, so why is it not possible for?
No. So that transform matrix you get from some other methods. Of course, you can write it in this way if you want to write it. Whenever there is a transform matrix, you can always write it. Right? But there is no representation. How to represent it? Okay. So then you have to represent like a 1-dimensional one. You say that 2-dimensional thing is like rods. You just say that this and this and this. Then you say that the matrices are not, how many type of matrices are there? Because there are 3 sides, q to the power 3. Because this can be any of them is 1, 2, 3, 4 q. This is 1, 2, 3, 4 q, right? So this is q to the power 3. So q to the power 3 lines are there. So you can represent each line, each types of lines are there. Q to the power 3 types of lines are there. Okay. For each line, if you represent by a matrix, so the matrix has index like D 3 3 3, D 1 1 1, D 2 2 3, then it is again a product. You can do that, that's okay. But then the number of matrices are infinity, because this line is also infinity. So then that is not useful. If the number of matrices are same, because the side variables are only 2, right? In a 2-dimensional model, for example, the side variables which is solved, the side variables are only 2. But to represent is a matrix product, you need infinitely many matrices. That is not useful. That is, of course, is not useful.
These two points is matching in 1D.
I guess you need to think a bit more about this, but in 1D there is a natural structure, right? You can just lay down these matrices and you can just keep on multiplying them like this, right? You think about this. In 2D, how do I think about this like that, right? That's the question.
Just if you write matrices,
Yeah.
wherever there is some side variable is written, you replace by a matrix. But then when you are done with it, what do you do with these matrices? You do not know what to do with them, because there is no operator which can bring you to a new matrix. And particularly when it is infinity dimensional, then right, you do not, these are harder.
But I guess you can restrict yourself to 1D.
I restrict to myself, it's always 1D. Okay, this method which I am talking about, let us work for today, it works only for 1D. Okay, no, actually it works for 1D. Most problems are only 1D. 2D it's not very easy. Okay. Okay, I'm just representing the matrices in a different way, and at some point I will come back to this. Okay, so now I will repeat these calculations. Why writing like that is easy. Okay. So now let us say that you want to calculate what is SK. What is SK? Expectation value. Okay, so in this representation I want to calculate what is SK expectation value. So what will be that? SK means kth plus the spin, SK can be plus or minus. So let us say SK equal to plus. That's what you say. What is the, this is a probability that SK, kth plus you have a plus. How often you see plus at kth site? That's what your question is. Okay, so if you want k equal to plus, then what you have is that all other places, it can be anything, right? Right? Any other place you can have anything. Every other place you can have whatever you want. Only at kth place you have this. So only at this you have. So basically anything can be represented by D or E, right? D or E means D or E, right? So at kth place, that means D of E to the power k minus 1, right? Here all this up to k minus 1 place you put whatever you like, okay? And kth place you want to put a plus. Plus means D. Okay? And how many sides? K sides are there, and then this is again D plus E to the power L minus K, and then you have a trace. Divided by trace of D plus E. Let me write it, D plus E to the power L. Are you getting this equation? Because you can see that this is all configurations which has plus at kth site, right? Here D plus, right? Plus, right? If you put all of D, if you can take from each of the term, then one configuration is all the plus here, and then this here it is plus and anything. So anything will come here. So all configurations fixing plus at kth site divided by all configurations. That's the probability. That's the way you measure probability. All configurations and all configurations which is k, which is plus at kth site, right? This is a number. So that's the way you are writing. This is becoming very simple, right? So this, this is the now. So you can say that this is. Let us say that because the results we know. Are you getting back there? So now let us write that. So this is D plus E to the power k. So this is T to the power k minus 1. Okay, and take one of the notations. One of the notations for D, let us say T to the power k minus 1, this is T to the power, let us make it little simpler. So this is T, and this is rotationally invariant. So because it is trace is there, so you can start with D. So I tested D, T to the power L minus 1, right? I mean this and that go, total is L. Length has to be always L. So this is trace of d t to the power L minus 1 divided by trace of t to the power L t to the power L. Okay. So that was the formula. Okay. So now, let us calculate plus instead of plus. If you want to plot minus, then instead of d it becomes e. Okay. So now, if you want to calculate expectation value of S, let us say S average, right? So instead, so then it will come at plus with plus sign, minus with minus sign, because S is right. I mean, that's what it comes. So then this will be d minus e. Okay. So S average is just d minus e. D minus e t to the power L minus 1. Okay. So trace of that divided by trace of t to the power L. No, I mean, no, I can just multiply, calculate it much easier, but I'm just saying that, showing that it was coming exactly like that, sigma z. So d minus e equal to just t sigma z, na? Yeah. D minus e times t to the power L minus 1. Now let us look at the notation of d. What is d minus e? So d minus e is t times plus plus minus minus minus. So this is t sigma z. Okay. So d minus e is just t sigma z, and t you can take here. So this is exactly equal to sigma z t to the power L trace divided by trace of t to the power n. So you don't have to go back to the sum and do the sum again, and it's coming very nice. It's okay with you, right? I mean, this is what we got earlier. It's a different thing that the whole calculation gives you 0, right? I mean, this is actually 0, right? This is, we calculated it and we find that this is 0. That's a separate thing.
I think the real utility will show up if you even put a magnetic field.
Yeah.
This is far simpler than.
Yes.
The transfer matrix still is a bit clumsy.
Yeah. But that is I can put that. Yeah.
Yeah. Just a comment. Yeah.
No, it is very right. I mean, because if you have anybody has done Ising model in 1D with a field, because then you know the complexity there, right? I mean, how messy it becomes. Okay. But here, if you have a magnetic field, what is Arnav saying that let us say that the Hamiltonian, let us change that minus h summation over I SI. Okay. So can I now find what is D and what is E? Right? I mean, these equations will still hold because these are pretty general. These equations will still hold. Okay. It just have to find T. Once you find T, right? I mean, what is T? So T, let us find what is T, right? I mean, what is the T matrix? T matrix can come, right? I mean, T ij is just e to the power. So let us write that. Okay. So now let us do this exercise. This is instructive. Very nice. Thank you. So you have a Hamiltonian H equal to summation over I minus, okay, and SI plus 1, okay, and minus summation over I H summation over I SI. But this I can write SI because this is a sum. I can write SI plus 1 divided by 2. Just write it again, right? I mean, this is just saying. So now this can be said, right? I mean, this is just function. So this you can write minus summation over I, some function. Actually, minus also I take some function of SI plus 1, right? I mean, you just sum it, right? And what is a, so this is, you can call T SI plus 1, right? So this you can write what is f SI plus 1? So this is equivalent to something like summation over I SI T SI plus 1. Okay, that's the way you write, right? I mean, this function. What is this function now? FSI is minus of SI plus 1. So FSI. Actually, let me write SS prime. Doesn't matter what they are. FSS prime equal to minus SS prime equal to minus. No. I did a mistake. Sorry. This is f of s. Let us write f of SS prime. So f of s prime equal to minus this minus SS prime, and this is minus h s plus s prime. I mean, this is just that. Okay. So, but then when you put in the partition function, you get e to the power h, e to the power beta h. Okay. So then e to the power beta h will give you. Is it okay? So e to the power minus beta, and these all these minus sign will go. So plus beta times summation over I. I mean, forget about that. Si plus 1. Okay, plus beta h times si plus 1 divided by 2. Okay, so that's the term. So this term you are identifying as T of S1 si prime, right? I mean, the summation over si becomes, because if you take a sum here, it becomes a product over I, right? I mean, because sum in the exponential become product of things. Okay, so this is the term, the total term. So the product of all these terms. So each term, this one you are representing as T of si plus 1, right? I mean, that's what you are representing. So these are the matrix element of T si plus 1. Okay, so T, if you take this is plus, this is plus. So what is the plus plus element of T? E to the power beta, and from here this is 1 beta h. So e to the power beta plus beta h. Okay, what will be plus minus? From here it will be 0, but here it will be plus minus is minus beta. So e to the power minus beta. And what is this one? It is for minus beta. And the other one is e to the power beta, because this is minus 1 and minus 1 now, minus. This is minus beta h. Okay, so that's the matrix. So once you know the matrix, use this equation to get D and E and calculate whatever correlations you want to calculate. Pretty clean, right? I mean, it's like a back of envelope, you can do this. It's not very difficult. Okay, you know the transform matrix, you find this. So now question that, let us keep these matrices here. Okay. Other thing I just wanted to comment out, we have calculated one transfer matrix which was with h equal to 0, that was symmetric. Okay. Here also it is symmetric. Okay. So the symmetric usually comes from a property of equilibrium, because in equilibrium the transfers in forward direction and transfers in backward direction, doesn't matter, right? So basically the transfer matrix is symmetric. Okay. Okay. And of course all elements are also positive, right? I mean, that is those are the property of transfer matrix, because these are, you are writing, it's a probability, each of them is a probability. So basically it has to be positive. So all elements are positive. This is finite dimensional and up to 2 dimensional, and it is symmetric. So these are the properties of this matrix. We remember that. Okay. So now can somebody tell me how to calculate, just I erase this now. Okay. So now can I calculate, let us say, the correlation functions. So correlation function, like it's like a joint probability. Like, you are all configurations. If you want, so for example, correlation function, I define one. Let us say plus plus. In the neighboring sign plus plus. Let us say. So how often you find in Ising model, right? I mean, you are in a stationary state. How often you find plus plus somewhere?
How is this probability? Because first e to power beta is clearly greater than normally.
No, but it is positive is greater than 1.
So e to the power beta
Or unnormalized. Unnormalized.
Oh, what's no, because right, I mean,
No, but see, it's like all coming from e to the minus beta.
No, it is right. I mean, it is up to only a normalization factor, right? Because the partition, what you call partition function is taking care of the normalization. That's what the trace of all configurations you are keeping only because of that. Because you should be using this one, without any hesitation, without bothering about normalization, right? I mean, you are keeping the partition function just for that below. Trace of rho or trace of t to the power L or whatever, that is just for the normalization, because then it's probability. Okay, so can I calculate plus plus in the neighboring side, for example? Just as a formula, like, can you just tell me what it will be in terms of the matrices? Any model, right? I mean, so now if you know the transform matrix, you know DE and you can fit it and you can calculate. So now what is plus plus expectation value in the neighboring side? So then, can somebody tell me trace of, can somebody prompt me? So trace of what? D square t to the power L minus 2, because this, why I am putting it first side? Because it can be anywhere, right? I mean, wherever you put, because of the trace in the ring, you can bring it always to the front one. Okay, so d square t to the power L minus 2 divided by trace of t to the power L. Great. So it's so simple, right? I mean, 2 by 2 matrix, you know all of them, you can calculate it. Okay, so now let us, so this is not, this is called the neighboring. So you can find how often you find consecutive 3 sides positive in Ising spin chain. You just put dq. You can calculate them. This is fun. You can calculate them, you can measure them. This is kind of one exercise everybody should do, right? I mean, if you know how to calculate them in computers, okay, try to calculate how often you see 3 consecutive spins in a Ising model of size 100 and temperature beta equal to let us say, yeah, whatever, 0.1. 0.1 is high temperature, let us say 1, beta equal to 1. Okay, you can calculate these numbers, compare what you get versus what you. So this is a very nice exercise. Okay, so this is only neighboring sides, but then you can calculate it at a distance r. Okay, so let us say that what is the probability, right, of finding a 2 spins, both of them are plus but separated by a distance r. You have a plus here, in a distance r you should be finding a plus there. This is also a correlation, right? So this is joint probability of finding things. So so what you want is that all configurations where these 2 places are plus divided by all configurations. That's the probability. This is joint probability, right? So can you say that, right? I mean, plus, right? I mean, plus and plus at I and plus at R, this expectation value. So this equal to trace of d, firstly d, and then t to the power r minus 1, because at the rth site you have, or maybe I can call it I plus r, then it is better, I plus r. Okay, then this is just d t to the power r, and then another d, because you want a plus there, right? So it's a joint probability of having plus at a distance r. D to the power, so d and then t to the power L minus 2, because these 2, and minus r, because this r. So that all of them becomes 2, and then trace of t to the power L. Okay. So correlations, finding the correlations are easy, right? I mean, this is, now you know why this function is a joint probability. Okay. So you can also call, instead of plus plus, you can call minus minus. Okay. So now you can calculate all of them. Okay. So now if you want to calculate, let us say that you don't bother about what they are. Okay. Generally the correlation functions are defined as SI plus R expectation value. Okay. It's not only that, it's the joint probability. So if R is very large, they kind of separate out. So you can also subtract what you get at R equal to infinity. Okay. So if you subtract, the whole function will become 0 at R equal to infinity. That's simply first. So basically SI plus R, you can call it SI expectation times SI plus R expectation. This you generally defined as correlation function. Okay. This is the general one, because if R goes to infinity, this is joint probability. So given some spin at here S, I mean, at a distance r, so they will just become the average, because they are not correlated, right? I mean, they are independent. That's an independent measure. So basically, this minus that, that's what you want to calculate. Okay, that's a correlation function by definition.
So this is also called a connected correlation.
It's also called connected correlation function. Yeah. Okay.
What would be the probability to get plus and plus at the first and the second side?
Probability to find the first and second side.
As both plus and plus. And so the first, when we have calculated plus plus, did we say that it's a probability to get plus plus anywhere or just the
first to sight, but just because it is a ring, you put it in D square wherever you like, you get the same thing. Okay, you can take also sum and divide it by L, but anyway it's just L. So one way to define it is you take a sum, doesn't matter where, you calculate wherever. So when you do your calculations numerically or wherever you want to do calculations, so if you are looking for plus plus, don't look at it one place, because one place is same as the other place. Calculate it wherever it is, count them and divide it by L, so that you get it at per side. You can do that, or you can just fix a side, right? You know, calculation wise, you know that this the same. 2 pluses here or 2 pluses there doesn't matter, because it's a ring. That's
second one, sir, if R is 1, we should obtain the first one, right?
R equal to 0. The distance is R. I'm not counting them. Depends on how you want to define.
If R is 1, we should get plus plus result, right?
R equal to 0.
No, R is 1.
R equal to 1 is.
Because it's I and I plus R, right? So he
Then
wants one side and the side next to it.
So then this is R minus 1. Na? Then I have written it wrong. Minus 1. Then it is plus 1. Yeah, okay. Then it is fine. Oh, that side, but this side is not counted. One of them is not counted, not both. So if this is I plus 1, this is RT to the power R minus 1. Okay. This part is fine. So now, if you want to calculate this one, SI can be plus or minus, this can be plus or minus. So there can be, if you make a product, this is plus plus probability with a plus sign, minus minus with a plus sign, and other two will be minus sign. And each of them you are calculating here, so you can calculate that also. Okay. So I will calculate, rather, instead of calculating this, for simplicity, I will take only one, just plus plus R, right? I just say that my correlation function, C plus, let us say, C plus of R. So this I say that plus at I and plus at R, plus at I plus R, minus plus average at I or I plus R, it is the same, just square, right? That's what I want to calculate, okay? And that is the correlation function. Okay. So now question is that, can I find the correlation? Hey, tell me. Hey, what's the time? How?
20 minutes.
Oh, okay. I thought I crossed 10 minutes. No, okay. Okay, great. Take it. I think I'm not doing bad. So, okay. So that's the correlation function. So I know how to write this correlation function. Okay. So now these are given. So on this one and this one, both of them I have calculated, and matrix formulas are known, you can calculate them. We will not do that. Okay, you could try doing it yourself. But we will argue how it will look like in general, right? Not in this model, because doesn't matter what the model is, right? I don't know the model, right? And the model, the representation of the model is by this, right? Because for any model, as I say, that you can always write for any model, we know that the correlation function look like that. General behavior of the correlation function. It's not that Ising model, we just do generally something. So plus corresponds to one particular variable, okay? Correlation of one particular variable at a distance R, okay? That's what we do. So if the system has n variables, some q variables, like I also say that, so let us say some variables I do not know, Ni equal to 1 to q, and I'm saying that, let us say that the transfer matrix formalism is there, and you know a transfer matrix. You can work with this if you know a transfer matrix. It's only the calculation part, okay? And for some, right, q variable I have already calculated a transfer matrix, so you can always calculate a transfer matrix, okay? So for the models which have transfer matrix form, this will work. Otherwise, you can write it. It's not that the formula is not correct, but you do not know what D and E are. Okay, the formula is always correct. Okay, so let us say there are variables q, and the corresponding matrix, they are represented by 1 by matrix D1, q by matrix D2, dq. Okay, and then 1, 2, so 2 by matrix D2. Okay, so this is the corresponding representation. So now the partition function in this case, this will be just D1 plus d2 up to dq to the power L trace. Okay. So that's your partition function. I mean, I don't have to know the model, right? I mean, I'm assuming that there is some d, some e exist for each of them. So this will take me all possible configurations, right? I mean, because this to the power L is there, I have to put a trace here, another bracket. Okay. So that's my trace. And then if I want to calculate, let us say to calculate one of them. One. We will calculate one, d1. Okay. So d1 is some variable. So you have, the system has some Hamiltonian, it's going to some kind of some stationary state which is in equilibrium, and in equilibrium you want to find out how, what is the correlation between correlation of this variable, what you call 1, at a distance r. That's what you want to measure. So the formula, like, you have the same thing. Can you write it now? Given this. Okay. So this, I also represent this one equal to t. Okay. So this is trace of t to the power L anyway. Okay. So this is my partition function, and this matrix is defined, this is also t, right? I mean, that's my t. So now the correlation function, like, 1 at I and 1 at r, I plus r, minus 1 expectation square. Okay. So this is this expectation I want to calculate, some variable. I mean, it can be plus, spin, or whatever, I do not know. So this is the variable I want to calculate. So this one, this expectation value, this I call it C1 of r. Okay, C1 of r. Let us see that how it will look like. So C1 of r, this equal to tell me, help me. So basically, one for first I write d1 because first one can be fixed anywhere. I put it at first side. So d1, and then t to the power r minus 1. Okay, that's the same thing which I am writing. T to the power r minus 1, again d1, and then t to the power L minus. Now can you plus L minus 1 minus r. L minus 1 minus r. Okay, so this is equal to trace of that divided by trace of t to the power L. I mean, I don't write trace of t to the power L all the time. I'll write just trace divided by z. Okay, that's this part. But I have to also take one expectation square, right? One expectation square is, right, I mean, minus trace of d1 t to the power L minus 1, just fix 1, divided by trace of, divided by z, of course, trace by z, and then I take a square of that. The whole thing has a square, okay, because that's expectation value of 1, and I take a square. So now I intend to calculate how this will look like. Okay, these are general systems and how it should look like.
Erase the square.
Or erase the square. No. I mean, I know what you are. Okay. So this is what I want to calculate. So now I just wanted to tell, right, I mean, how it will look like. Okay. So now let us look at first z. Z is t to the power L. Okay. So first one, let us look at how z look like, behavior of z. Okay. The partition function z. So this equal to trace of t to the power L. It's on a ring, 1D ring. This model works for 1D ring with q variables. I don't need it at this stage. I have not specified what is the Hamiltonian. Trace of t to the power L. Okay. So this equal to lambda 1 to the power L, because this is t. Last time I just said this is sum of all eigenvalue to the power L. Lambda 1 to the power L, lambda 2 to the power L, and lambda q to the power L. Because there are q variables, I am expecting a transfer matrix which is q dimensional here. Okay. Yeah, but this dimension, because I have not specified, so I can put it whatever. Yeah. So lambda makes whatever. So whatever the dimension d. Okay. So d is the dimension of transfer matrix. D T equal to dimension of T. Okay, dimension of this transfer matrix. Okay, so whatever. So this can be written as lambda 1 to the power L times 1 plus. Oh, okay. So if you have eigenvalues, how, right? I mean, one of them is largest. Okay, I am talking the largest. Everybody agreed on this. Nobody has a disagreement. If you have eigenvalues of a matrix, one of them will be largest. What if they are complex? It can have two matrices with two eigenvalues, both complex, na? So then how do you compare? Right? No, okay, I mean things can happen, but no, you should know, right? I mean these questions are there, but I am just saying that if the matrices which I am talking about here, it is I am talking of equilibrium matrices for the time being. Okay? Okay? So the matrices, let us look at the matrices, and these are all positive, these are positive elements. Okay? And this is symmetric. If the matrices are symmetric, it will have real eigenvalues. Okay? I mean that's the point. Okay? So it is a symmetric matrix, so we will have real eigenvalues. We don't have the bothersome, right? I mean, even if they are not symmetric, I will, right? I mean, I am demanding now. If you go to some other thing, non-equilibrium or something, even if they are not symmetric, there will be a largest eigenvalue as long as it is finite dimensional, okay, and positive. I mean here anyway, positivity you cannot get out, right? I mean it has to be a matrix with positive elements, but that is guaranteed. But only thing is that as long as it is finite dimensional, there will be the largest eigenvalue will be real, and it is distinct from the next largest. Okay, so that's a theorem for that. We'll come little later details about this, little details. Okay, so among them, whatever is the largest, I call it lambda 1. Okay, because I have a choice to make what is lambda 1. This one is not that one. No, I mean this one is called lambda 1. I replace it by lambda max. Okay, so I call it lambda max, whatever is the maximum to the power L, and that I calling it to 1. So lambda 2 plus lambda 2 divided by lambda 1 to the power L plus lambda 3 divided by lambda 1. Okay, the rest of them I have arranged in terms of, let us say that modulus of, if it is complex I arrange them in modulus value, or right, I mean if it is real I arrange them in decreasing order, right? The largest and next largest lambda 1 like that. So lambda 2. So I am assuming that for T real, T equal to, if T is real, okay, so sorry, T is symmetric, and I am also assuming lambda 1 is less than lambda 2 strictly. This one is strict. Lambda 2 less than equal to lambda 3 less than equal to lambda 4, like that up to lambda t. The first one is distinct. Yes. Sorry. Lambda 1 is greater than that, greater than equal to that, greater than equal to that. So okay, so I arranged. This is my names, naming the eigenvalues in this sequence. Okay, so then I said that lambda 2 by lambda 1, lambda 3 by lambda 1, or lambda max. Okay, so this is lambda max, this is lambda max, this to the power L, and it goes on. Okay, so this one, because eventually I take a system L goes to infinity, this one in L goes to infinity limit. This is if it is largest, and strictly it is greater than this. Okay, that I am not proving. I mean for the time being you take it. Okay, take it granted that in these matrices the largest, the examples which you know, that e to the power beta plus minus e to the power minus beta. So the largest e to the power beta plus e to the power minus beta, that is always larger than the second one. Cos hyperbolic versus sin hyperbolic. Cos hyperbolic always greater. Okay, so this one. So now if there is a clear distinction between the first one and the rest, okay, first one and second one at least. So basically this divided by that is clearly less than 1. Okay, so then what will happen is that this one, for L goes to infinity, this will vanish. Okay, so this goes to 0. All of them goes to 0. Okay, so basically this tells you that the partition function is just lambda max to the power L. Okay, for large L you can safely assume lambda max to the power L. Okay, and how big is L, right? I mean because this is exponential function, something to the power L is exponential function, it is quickly decay. So large doesn't mean that you have to say that 10 to the power 50 or 10 to the 20 or something. Like if it is 100, it is quite small. E to the power 100 is small. e to the minus 100. So because this is small, okay. So this is exponential function, it is pretty small, but 0.01 to the power 100. So right, it's very small, okay. Even 0.99 to the power 1000 is like, it's small, right. First term is just 1 and second term is also 1 by that is 0. If you expand it, even 1 minus, so it's 0. So very small, these numbers are very small, okay. So you have a partition function given by that, okay. Okay, I think, how much time I have? I think this one we calculate little later. So let us continue with the partition function itself, okay. So what can happen? So what can happen, if the partition function is like that, okay. So partition function is this, okay. So now let us talk a little bit about the Hamiltonian. Okay. So it doesn't matter what is the Hamiltonian. The Hamiltonian has some parameters, like I do not know your variable. Of course, there is an interaction between n1, n2, right? Whatever the value here, there is some interaction. But the interaction will have interaction strength, like some J1, J2, J3, some interaction parameters. So the Hamiltonian will depend on these parameters, some J1, maybe J2, some parameters. So all the parameters of the Hamiltonian, those are there, okay. So now, if the Hamiltonian has some parameters, your eigenvalues of t, like you want these eigenvalues, the eigenvalues, all eigenvalues are functions of those parameters in the Hamiltonian, like J1, J2, whatever, all these parameters. But then there is extra parameter, beta, okay. Because when you write your partition function, you also introduce another parameter beta. So all parameters of the Hamiltonian and a parameter which you introduce because it's the system is in temperature T is beta, okay. That comes here, temperature. So the partition function is, I know, and I will not distinguish what is the parameter, okay. But any of the parameter you change, then the behavior of the eigenvalues will change, okay. So I will plot the eigenvalues with respect to some parameter. I don't know which one. You can take whatever, which one. So some parameter, I call it general parameter, I call it A, okay. A is the generic parameter, any of them, I don't know what. So I'm plotting it with A, okay. So now question that what do you expect? So first one, okay. First one is like that, something, I do not know what, some function, maybe like this. Some anything you want to plot, right? It's just something. Okay. The second one can be like that. Third one can be like this. Fourth one like that. Some functions. Okay. These are how the eigenvalues of the system changes with this. But why I'm right? All this crossing I'm doing, I'm not touching this one. Okay. And that's the theorem. As I say that the theorem, there is a so the matrices. This is the eigenvalue. So this is what is that one. This is let me write it. This is lambda 1. This is lambda 2. This is lambda 3. Okay. So these kind of assumptions will not hold anymore because if you change parameter at each parameter, this kind of which is lambda 1, which is lambda 2. So this you for the time being you switch off. Like you are following like whatever is the largest at some parameter value, you ordered it here and you are keeping this name onwards. Okay, just keeping that name. So this lambda 3 goes like that, lambda 2 goes like that. This can happen like that. Okay, I'm assuming all real, and with A there is some change of parameter. Okay, but the largest one is always unique. Okay, so let me state the theorem. It's called Perron. Somebody wrote Frobenius Perron. Okay. I call it Perron-Frobenius because Estado Perron-Frobenius. Okay, Perron-Frobenius theorem. Okay. Okay. So what I state for this theorem is smaller than what actually it is. Okay, I don't need all the rest of that one. I know this theorem will work even in a weaker condition than that. I will put a very strong condition. Okay, the condition is that if a matrix is largest eigenvalue value of a finite dimensional symmetric positive symmetric matrix is I'm skipping some. So matrix is non-degenerate. Okay, and this is a very important theorem, and I will explain you why. Okay, so what it says is that if a matrix is all elements are positive and the matrix is finite dimensional and symmetric. Okay. Actually, the bigger theorem is all if the matrix is irreducible, but that's very difficult. Let us put conditions which you can check easily. So this is, for me, I need only that. Okay, if the matrix is irreducible, this still work. Even with zeros. Okay, so even with zeros and even with symmetric or what asymmetric, everything works. But I'm not going there. Okay, this is, let us say that this is the smallest part of it. So finite dimensional, positive. So positive can, okay, and this is non-degenerate. Okay, so the largest eigenvalue, if it has to be on the top always. Okay, that's the point. So nothing can touch this eigenvalue. Any other eigenvalue cannot touch this. The one which is largest remain largest. So now let me say that what would have happened? What is this consequence of this theorem? Okay, what would have happened if they cross? Okay, so let us say that I just take two more minutes. So let us say that some eigenvalue, let us say lambda 2 is like that, lambda 3 is like that. Let us call it lambda 4. This goes and cross like that. Happens. What will happen? Okay, if this happens, what you say is that partition function, you know that your partition function is only lambda max to the power L. Okay, so lambda max in these regions, regions of A, lambda max is just this given by this equation. So you are following this. Your lambda, this is your, what I'm drawing is lambda max. Okay, and then here lambda max is that. Okay, so your partition function, you come up to this, will follow this function, and after that suddenly the partition function changes its behavior and you have a different functional form. Okay, so this point you have, you cannot analytically continue in that direction, right? Whatever you are doing from this side, you cannot go to the other side. Okay, and that's what we call a phase transition. There is no analytic, so there is a analyticity breaking at this point. The partition function in one side is described by one kind of function, the other side is described by some other function. Okay, and there is a discontinuity here. So what is the kind of so basically that is a phase transition. So eigenvalue crossing corresponds to phase transitions. Okay, so what do we say? This theorem specifically rule out situations whenever you have a transfer matrix like that, and you have whenever there is a local interaction, you can always find a transfer matrix with finite variables, and then the matrix will be symmetric because you are talking of interaction. Like I interact with you, you don't interact with me is not a physical situation. Like it's the same situation, right? So basically it's a symmetric matrix. Okay, so it's a symmetric positive matrix, and so in this situation, as long as it is finite, you cannot have a phase transition. Okay, so 1D Ising model will not show a finite temperature phase transition. Why finite temperature? Because if you put temperature equal to 0, then there will be zeros introduced there, right? So that is not something which you want. Okay, t equal to 0 means beta equal to infinity. So these elements will be 0. So the theorem has nothing to say. It's not saying, theorem doesn't say whether there is a phase transition happen. When it will happen, it doesn't say. It only rule out the possibilities. Here it will not happen. Okay, so that's what eigenvalue. So then only one other point I will just make and then we'll stop. So if you go from here to here, what kind of discontinuity we have? So you can see that lambda max, derivative of lambda max in this particular situation will have a change, right? Because the slope here was like that and here it was like that. Okay, so the slope will have a change, right? So if you plot the slope of lambda max, or you can, instead of plotting the slope of lambda max, you can plot a slope of log of lambda max. Lambda max, any function and its logarithm has the same behavior in terms of increasing and decreasing. So the derivative of lambda max will have a discontinuity at A. Okay, first derivative itself, because the slope itself is a discontinuity. Okay, so that will be so basically instead of lambda max, let us say del by del A of lambda max. Instead of lambda max, you can put also a log of lambda max. But log of lambda max is just log of z, right? I mean, log of z is L log of lambda max, and log of z is like a free energy. Okay. So what we'll have is the first derivative of the free energy will show a discontinuity. Okay. So that's the first order transition. So in case you are worried, curious to know second order transition, can you tell me what what situations will give you a second order phase transition? Yes. So the first derivative will second. So basically the situations when you have second order transitions, it will go like that, right? I mean, so there is a. I mean, let me plot it a little better like this. This is one, and the second one or some other one which will come here and go like this. Okay. So the point is the derivative has to match. And the usual, basically the derivative has to be 0 there. And the derivative with respect to this partition function, derivative with respect to that has to be 0. And the derivative is usually the order parameter, right? Which has a gap at a first order transition. Now the gap is not there because the derivative will be 0 from this side, from the other side. Okay? It's on the next derivative. Next derivative of the order parameter is just fluctuations. Okay? Fluctuations or susceptibilities. If this terminology is not clear, we'll continue it little later, but for now I stop. So second derivative will be discontinuous or non-analytic, particularly diverging actually. So then you have a second order phase transition. So what we find here through this theorem is that 1D short range interaction cannot have a finite temperature phase transition. So that's the partition function. Okay, this is general one. So we'll also talk about what is the general behavior of the correlation function in any such models. Okay. Using this technique. Okay, so I think that is in my.
The closing of the gap
Huh.
as a function of S will have some power law dependence.
Yeah. No. So this will be right. I mean, a minus
The gap will go as L to the power some
nu 1 by nu or nu, right? I mean, because the closing means a minus AC. So that's your epsilon. So your length scale is a minus epsilon to the power minus nu. So that's the
that will appear in the correlation.
Correlation of length. Yeah. For finite system, it's a correlation length. That's the only length scale. For finite system, that will show. So there is this is an advanced question. No, I mean, ignore the question. No.